by referring the book Reinforcement Learning and Introduction by Suttan and Botru and the classes from Shashisha. A typical MDP we can write as it is set of actions, states, actions, transitions, rewards, and the next state. The transitions, either they may be known or unknown, depending upon what kind of environment we are taking, either it is a model based or model-less environment. So, if we are having the transition in a model based, these are called as planning. If the model is not having, that is, you can take as model-less models, then we are going to solve this MDP by using learning. We will start from a state that is S0. Depending upon the policy, the agent will take some action A, and we are going to take the assumptions or planning. Depending upon that, we are going to have the change in the state that will take as S dash with a reward of R. So this transition from S0 to S0 to S dash, either we may do using planning or learning. Planning is nothing but these transitions if you are considering the environment which is a model based. If you are not having any idea on environment, then we are going to be consider this model less, where we are going to take the learning mechanism for solving the MDPs. So in real world, to solve MDP, the transitions are always unknown. So learning will be takes place. So in this learning, we are going to the sample environment. Let us assume there exists a distribution T for which we don't have any access to it. The way we used to estimate it is called as a sampling. So this samplings will be takes place the distribution of transitions where we don't have access for it. Then we want to estimate. How we will estimate is by doing the sampling. So where we are going to have a MDP, which is a set of state, action, transition, reward, and the change of state. So this T we are going to do the sampling. So let us consider we are in initial state which is S0. Then we will take some action A1 and the change of state is S1. If action is A2, the change of state is to S2. If action is A3, we may change the state to S3. So first initially we will apply some policy phi and we are going to get some reward that will take as R1. A new policy will be considered that is a phi dash. Then we will get the new reward which is R2. The change of the policy is phi double dash. We may get reward R3 and we may get a new policy. So this iteration will be takes place until we are going to get the optimal policy. For every policy, whatever the reward which you are going to get, that we are going to accumulate for evaluating the value function V of S or Q of S. The value function V of S is nothing but it is the sum of the rewards which we are going to be take based on only states. Then this will called as the value function V of S. Whereas Q of SA is it is the sum of the rewards which is based on state as well as action. So in the sample, it is consist of the current state ST the current action AT, and the current reward RT, the next state which is S of t plus 1. So this S of t we will call as the start state or initial state, and the S of t plus 1 is nothing but the next state. This set from the start state to next state, we will call them as experiences. So every interaction with the environment gives an experience to learn about the environment. Here, the basic assumptions which we are relaxing for this model less environment is, the first one is we are going to be consider the complete information about the environment. The second assumption is we will take the some probability of a change of state from S to S dash for a particular action A. So estimating the value function and finding the optimal policy based upon the experience we are going to be considering. So the Monte Carlo methods basically we use for this model-less or sampling method. We will also call the Monte Carlo as the simulation methods or sampling methods. We can also call this one as simulation methods or sampling methods. The Monte Carlo method mainly works based upon the averaging of sample returns. In Monte Carlo, for solving MDP, the learning we have two steps. In the first one, we are going to use for prediction step, where the prediction step it is for estimating the value function. Either it is V pi or Q pi. The second step is the control step, where this control step it is used for improving the policy. So this Monte Carlo learning mechanism also following the general policy iteration, that is GPA structure only. So here we are going to take a sample where it will start from S with an action A and reward R. We are going to get the next state as S dash. Then new action is S dash. New reward is R dash. And the next state is S double dash. So this will be continued until we are reaching the terminal state. So S3 we are going to be considered as the terminal state. So when we are learning using a Monte Carlo, here main from which state we are starting is considered, it is immaterial of where we are going to have the terminal state. And this prediction step, it is same as that of the evaluation step. Here we are called it as prediction as we don't know the methods or model of the environment, and it is an estimate or prediction step for value function V pi or Q pi. For a given policy, we are going to find the value function V pi or Q pi. The second step is the control step. This is same as that of the policy improvement, where this policy improvement we can consider as that is phi of s is equivalent to arg max of whatever the actions which are going to generate the value function q of phi for a state s and action a. From start state s till the terminal state, this entire thing we are going to be considered as one episode. So in learning, we are going to take a few number of episodes. For all the episodes, we are going to find out the value function, which is nothing but the accumulated reward from the starting state to terminal state. Now we will consider one example. So let us consider here the input policy pi, where if we are in state B, we will take the action towards a left side, and for state C, we move towards left side. For E, if you are in E, the next state is we are going in the upward direction, and the terminal states are state A and state D. Let us assume a few observations on the episode. We are going to consider four episode 1, episode 2, episode 3, episode 4. In episode 1, starting from the state B, take east direction, which is nothing but towards the left side. We will reach the next state is C, and the reward is minus 1. Next, from C to, we will take towards left side, that is nothing but east direction, and we will reach the next state is D. For this transition, the reward is minus 1. From D, we have a exit, that is terminal state X, and the reward is plus 10. Whereas in episode 2, we will start from the state B. We will take the action towards each side, that is what move in left side, reach to the state C with a reward of minus 1. From C, again we will take action towards each side, nothing but left, and we will reach to a state D with a reward of minus 1, and D, which is a terminal state X with a reward of plus 10. In episode 3, we will start from a state E, take an action towards north side, which is nothing but moving in upward direction, reach to a next state a C with a reward of minus 1. From C, we will take a action towards moving east side, nothing but towards left, and reaching to a D state with a reward of minus 1. From D, we go for terminal state, exit state X with a reward of plus 10. In episode 4, we will start the transition from the state E, and we will take the action towards upside, that is nothing but north, and we will reach to a state C with a reward of minus 1. And from C, we will take an action towards east, and the next state is A with a reward of minus 1. And state A, we will take an exit with a reward of minus 10. Now, if you observe, as per the input policy, when you are in state C, what is the action we can have is only left. But if you see in episode 1, episode 2, episode 3, it is following the action is east state only when we are in state C. But when it comes to episode 4, the action is east, but the reaching to a state which is a A. As per policy, we have to reach to D, but we are reaching as per episode 4 to reach D. This we will call as noise. In all these cases, now we are going to consider the evaluation of value function for all the states. So what are the various states we are having? We are having the state B. So we are going to evaluate the value function for V of B as well as for state C. state D, and state E, and state A. So always we are going to start from a start state S3. We will reach to the next state S plus 10 with a reward of R by taking some action. Then we will get some more reward R2, where we are going to change the state is S of t plus 2, and we are going to be moved until the terminal state. So in our example, the terminal state is either state A or the state D. So here the various states we are having are state A, the state B, the state C, the state D, and the state E. For value functions, we are going to consider for state A as VA, for state B as VB, for state C as VC, for state D as VD, for state E as V. So now our objective is to estimate what are these value function. So how we are going to consider all the value function is we have to set all the episode for a particular state as start state, and we have to traverse through the episode to reach the terminal state. Till that point, till that point, whatever the rewards are there, those rewards we have to average in how many episodes it is existing. Now we will start for state B. The value function is V of B. So the first task we are going to consider is the estimation of the value function for state B. Now if you observe B, it is existing in episode 1 and episode 2. So for estimating the value function VB, we are going to consider the rewards in episode 1 plus rewards in episode 2. As it is existing in only 2 episodes, we will take the average by dividing this one to minus 2. Now we will see with respect to episode 1. In the episode 1, the start state we are going to be considered as B, and we are moving to the next state as C with a reward of minus 1. From C to D with a reward of minus 1. From D to we are going to exit, that is nothing but the terminal state, which is equivalent to plus 10. So now here the accumulation or the sum of all the rewards is equivalent to minus 1 plus 10, which is going to result as the total reward is 8 for episode 1. Similarly, we are going to evaluate for episode 2. So in episode 2, we are going to start from the state B, reaching to the next state, which is C, with a reward of minus 1. From C, we will move to a state D with a reward of minus 1. From D, we go for the terminal state for exit with a reward of plus 10. So now in this episode, the accumulated reward, this I will take as sum of R1 and sum of R2, which is corresponding to episode 1 and episode 2. So the sum of the rewards is minus 1 plus 10, which is equivalent to 8. So the value function of B we can calculate as the sum of the rewards corresponding to episode 1, that is R1, plus the sum of the rewards for episode 2 divided by the total number of episode where B is occurring, which is equivalent to 2 here. So the sum of the rewards for episode 1 is 8. So 8 plus the sum of the rewards for episode 2 is 8 plus 8 divided by total episode is 2. So which is going to result 8. So this is the value function for B, that is V of B, we will write as 8. Now we go for finding out the value function for A also. So now we will estimate the value function V of A. Now if you observe, the state A is not existing in episode 1. In episode 2 also, A is not occurred. In episode 3 also, state A is not present. In episode 4, we have value state A. So if you start from state A, we have only one transition, that is towards exit, and with a reward of -10. So the value function for evaluating for state A, we are going to be consider the sum of the rewards for episode 4 divided by, as the state A is existing in only one episode, we will divide this one with 1. So now the accumulated rewards is equivalent to, for state A is equivalent to -10. So now the accumulated reward is -10 divided by 1, which is going to result to -10. So now the value function for A is equivalent to minus. Now we go for estimating the value function for C. Now we will estimate the value function for state C. Now if you observe, the state C is exist in episode 1. It is also present in episode 2, episode 3 and episode 4. Now we will find the accumulated rewards for E1, episode 1, episode 2, episode 3 and episode. So in episode 3, the start state is C we are considering. The next state is D with a reward of -1. From D to the terminal state, that is exit state, with a reward of +10. So here the accumulated reward for episode 1 for C state is equivalent to -1 plus 10, which is resulting to 9. Now in episode 2, we are going to start from a state C reaching to state D with a reward of -1. From D to exit state with a reward of +10. Now if we calculate the total rewards for episode 2 for starting state is C, we can write the accumulated rewards is equal to -1 plus 10, which is resulting to 9. Now in episode 3, we consider the start state is C. We are reaching to next state D with a reward of -1. From D to exit state with a reward of +10. So the accumulated reward R3 is equivalent to -1 plus 10, which is equivalent to 9. Similarly for episode 4, in episode 4, the start state is C and the next state is A with a reward of -1. From A to the exit state with a reward of -10. So the accumulated reward, that is R4, we can consider as -1 minus 10, which is equivalent to -11. Now for finding out the value function for state C, we are going to average all these rewards. Reward for episode 1, sum of the rewards for episode 2, sum of the rewards for episode 3, sum of the rewards for episode 4 divided by total number of episodes is 4. So now it is going to result as 9 plus 9 plus 9 minus 11 divided by 4, which is resulting 16 by 4, which reduces as 4. So the value function for C is equivalent to 4. Now we are evaluated. So now we evaluated the value function for A, value function for B, value function for C. Now we will estimate the value function for D. that is V of D. Now if you observe, D is a starting state in episode 1, episode 2, episode 3. So we have to consider the rewards in episode 1, episode 2 and episode 3. Now if you consider episode 1, in episode 1, if we start from state D, we are reaching to the terminal state with a reward of less than. Only one state transition we are having. So the sum of the rewards is equivalent to plus 10 here. In episode 2, if you consider the start date is D and we are reaching to the terminal state which is exit with a reward of plus 10. So for this episode, the sum of the rewards is equivalent to plus 10. For episode 3, if you start from D, we are reaching to the terminal state which is exit with a reward of plus 10. So the sum of the rewards is equivalent to 10. Now for finding out the value function for D, we have to find out what is the average of all these episodes, which is nothing but summation of R1, summation of R2 plus reward accumulated, which is in episode 3, divided by total number of episodes is 3, which is equivalent to 10 plus 10 plus 10 divided by 3, which is resulting 30 by 3, which is equivalent to 10. So the value function for the state D is equivalent to 10. Now we go for estimating the value function for state E. Now here we are going to estimate the value function for state E. Now state E is not present in episode 1. The state E is not present in episode 2. The state E is present in episode 3 and episode 4. So we are going to consider episode 3 and episode 4 for evaluating the value function V of E. So if you consider episode 3, if you start from state E by taking an action that is not, we are reaching to the next state C with a reward of minus 1. From C to D with a reward of minus 1. From D to exit with a reward of plus 10. So now for this episode, for start state as E, the accumulated reward is equal to minus 1 plus 10, which is resulting 8. Now we will consider the episode 4. In the episode 4, we will start from state E. We will reach to state C with a reward of minus 1. From state C, we go to state A with a reward of minus 1. From state A, exit the terminal state with a reward of minus 10. So the accumulated rewards is equivalent to minus 1, minus 1, minus 10, which is equivalent to minus 12. So for finding out the value function for state E, we can write as V of E is equivalent to sum of the rewards in episode 3 and sum of the rewards in episode 4 divided by two states. So we'll divide with 2, which is resulting 8 minus 12 divided by 2, which is equivalent to minus 4 divided by 2, which is minus 2. We have to take infinite number of samples so that we can set better policy than the current policy. So estimating of each state are independent. The estimate for one state does not build upon the estimation of any another state. Here, for estimation, there are two kinds of variance. The first one is we are going to be considered as first visit. The second one is every visit. So these are the two variants we are having. In the first visit means we will start from some state B. We move to some other state until the terminal state. So where we are starting, only this point we are going to be considered as first visit. If it is existing further also, let us consider after some iterations, we may be reaching to B again. We may be reaching to B again. So for estimation of B, we are not going to be consider these two cases. Only this case we are going to be consider. This we will call as the first visit variant. What about every visit means we are going to evaluate the value function for B wherever it is existing. So now here it is existing for two cases. So now we will take this one as two estimate. One is from the starting, the second one which is from middle. So from here to terminal state, we will take as one episode. From the starting to end, we will take as the two episode. So sum of all these two entries we are going to be considered as every visit. The basic goal for any variant, either it may be first visit or every visit, is we have to estimate the ultimate reward. So in first visit, find the sum of the rewards with respect to first visit of the state. In every visit, we are going to take the sum of the rewards of every state occurrence as one episode. So if any state occurs two times, so we will consider as two states. If it occurs for three times, we have to consider as three episodes. Now we will see the algorithm for this. The input we will take, here it is a policy pipe, consider a policy pipe which has to be evaluated. This is the input. Next we go for initialize the V of S for any number of states which are existing. So where S is belongs to the state space S. So how many states we are having? That many number of entities we are going to take in V of S. So V of S you can take as a list of entities where we will initialize for all these states is equivalent to 0. Here the length of the V of S is equivalent to the number of states existing. Next, we are going to find out the return list. The return list is an empty list for all the states which are existing in the state space S. Usually, we will take like a dictionary kind of thing. For every state, we will take key value as state and what are the rewards which we are going to have, that we will take as a reward list. So let us consider how state S0, S1, S2, which will have the rewards. I'll take this one as R1 reward, R2 reward, R3 reward. S1, if it is occurring for multiple times, R1, R2, R3 corresponding to state S1. For state 2 also, reward R1, R2, R3, like this we are going to be considering. So here we are going to loop forever, and this we are going to be estimate for each episode. So in this episode, what we are going to be consider is, first we will generate an episode for a particular policy file starting from S0 state with the action A0, reward R1, next state S1. So like this, we are going to be estimate till the last state. and return what is the value of g. So for each loop step episode from t is equal to t1, t2, t minus 1, t minus 2, we are going to take till 0. Hence, t will start from the last time state. And the g we are going to be considered as the g is updated with the reward function with the previous estimated rewards plus the new reward that is r plus 1. So this is value function, old value function, multiply with the discount factor and the current reward rt plus 1. Unless st, that is current state, appears in S0, S1 till st minus 1, we go for appending g to return. Once we have got all the rewards, then we are going to estimate the V of S is equal to, which is nothing but average of the rewards for a particular state. So as model is not available, we have to focus on estimating the action value Q rather than value. So as to calculate the optimal policy, the optimal policy 5 star is equivalent to the arc maximum of all the actions, the value function Q S comma A, which we can write as, which is equivalent to argmax of all the actions, where Q of SA, the value function, we can write as summation for all the states, P of the next state S dash comma R, such that for a given state and action, multiply with the current reward R plus gamma times of the previous state value. So for this, we used model of the environment. For getting this probability, we need the model of the environment. So Q, as it is, depends upon both state and action. So the value function Q will be of size S cross A, whereas the value function will be depends upon only the state. So the value function size is equivalent to S. If you are representing this one as a matrix. What are the advantage of Q and V is the value function Q is faster, but it requires more memory. If you see the size, we want to store S cross A entities, so here we require more amount of memory. For estimating the value function, it is slower compared to Q, but it requires less memory compared to. So in Monte Carlo prediction, we have value function V of S, where V of S is a set of the values, that is V of S0, V of S1, V of S2, like this the value function until the terminal state S2. So we will run the prediction step to improve the policy, and we know the improved policy is the optimal policy pi of s is equivalent to arg maximum of actions A for Q of S. So when we start from a particular state S, we have always applied the same action A of t to reach S dash so that another actions will not be considered. By this, we can not explore more about the environment. Let us consider we have a state S and we have multiple actions like this is A1 and this is A2. One more action is A3. When you take action A1, we are going to reach S dash shape. When you take action A2, we are reaching S double dash shape. When you take action A3, we are going to reach the next state, which is S triple dash. So let us assume whenever you are in a particular state S, and if you are always taking a particular action A1, so it has to reach the state S dash so that the another actions will not have much importance. So because of this policy improvement mechanism, we are restricted multiple actions from a particular state S. So the policy become deterministic policy. If most of the time or if you take 100% of the time the transition is from S to S dash only we are taking, then this it is called as a deterministic policy. So if we have a deterministic policy, what are the disadvantages? Never we will take for particular state S, we won't take action A2, action A3 and we won't reach S dash and S double dash. So in this case, that means whenever you take a deterministic policy, you can't explore the environment fully. Why we are not exploring more means because always the transition is fixed. Whenever you reach S, by default we will take action A1, we will reach to S1. The remaining actions we are not going to take. So for solving this, that is solution for this one is we are going to create a stochastic process. This stochastic policy, we will also call this one as soft policy. Let us consider now the distribution probability of the policy. That is pi of the policy for action A1 from state S is equivalent to 1. That means entire probability is we are assigning to action A1 only. For action A2 from state S is equivalent to 0. The probability of taking action A3 in state S is equivalent to 0. So this we will call as deterministic policy. So as the probability of action A2 and action A3 is 0, so we can't explore from state S to S double dash and S triple dash at any point. To overcome this deterministic policy, we go for a distribution changing with soft policy. So what this soft policy will do is instead of assigning the probability as 1, 90% or 95% of the probability, more chances will be given for action A1. Some negligible amount of transitions we are going to take for A2 and A3. So to address this, we have epsilon greedy approach. Where this epsilon greedy approach, we can also call this one as soft policy. or we can also call this one as stochastic policy. What is the major difference you'll get is if you take any policy for a particular action A from any state Si, this I'll take as Aj, this is always is greater than 0. So no probability will exist from taking any action from particular state will be equivalent to 0. So, thank you. So now we have discussed the Monte Carlo prediction. In the next session, we will see the soft policy, which is the epsilon greedy policy, as well as we will see a few more terms like exploration and exploitation. Thank you.